pressure of a gas is very dependent upon the temperature, the volume of the container, and the amount of gas. And so we would like to know how we can express the pressure as a function of those variables. And so this leads us to a gas law. So this is just a mathematical expression of the functional dependence of the pressure upon temperature, volume, and the amount of the gas. So the simplest gas law is called the ideal gas law, and it has the form pressure times volume is equal to the number of moles of the gas times R, the ideal gas constant, times the temperature. So P is pressure, V is volume, N is the number of moles of the gas, R is called the gas constant, and T is the temperature of the gas. So this is a simple law. So this solving for pressure would give nRT over V. Now R is a constant, and so there are four things that can vary: pressure, volume, temperature, and the moles of the gas. So knowing any three, we can solve for the fourth. So if we want to know the volume, we say volume is equal to nRT over the pressure. If we wanted to know the temperature would be pressure times volume over nR. And if we wanted to know the amount, N, that's equal PV over RT. So we can simply solve for any four of these variables. Is start with the ideal gas, that's an N, not an M, nRT, ideal gas law, and you can solve for any of the four variables. Now the ideal gas law makes some assumptions about the gas. And some of these assumptions are fairly drastic, and so the ideal gas law doesn't work very well in some circumstances. And later on in other courses you'll correct for the ideal gas law, but we'll use this simple form for now. So the assumptions are as follows. The gas particles are point masses, which means they have no volume. So they have mass because they're an atom, but we're saying that they're so small that they don't take up any space. That's an approximation. It's not a real, it's not real, but we're just assuming that if we have a large container relative to the amount of gas, then the gas occupies very, very little volume of the actual container. The second assumption is that all collisions are perfectly elastic. That's just saying there's no internal structure that can accept or give off energy. An example of a fairly elastic collision is like pool balls, where you can put English on the pool ball and all the kinetic energy from the cue ball can be transferred to another ball on the pool table. So they're hard spheres, and so there's doesn't allow for energy to be transferred much internally. An example of a non-elastic collision is if you threw a a blob of mud against the wall. The mud's just going to splatter. It's not going to bounce off the wall really, it just splatters and sticks to the wall. So all the kinetic energy goes into deforming the mud ball. So that's an example of an inelastic collision. So the final approximation is there's no forces between the gas particles, which means no attractions. They don't attract each other or repel each other. So this is an approximation. In reality, when gas particles start to get close to each other, they attract each other a little bit through the forces, Coulombical forces, due to the electrons and protons in the atom. But we're neglecting that for the ideal gas law.